Good afternoon. Okay, till now we have seen gate level implementations. Just for those people who have joined today, we started with what is digital system, how is it different from analog, what are the advantages of digital. Then we talked about number systems, various number systems, binary, octal, decimal, hexadecimal. We also talked about conversion from one type to other. We also talked about codes. Why are codes required, like Gray code, ASCII code. We talked also about complement numbers, first one's complement, two's complement, how it helps, how they help in subtraction, because two's complement or one's complement subtraction is same as addition. The point is you can have the same hardware called adder, you can also use for subtraction, that is easy for the implementation part. Then we talked about basic gates, three types of gates. One is the fundamental gates, these are AND OR inverter. We talked about derived gates, NAND, NOR, exclusive OR, exclusive OR, exclusive NOR, and so called universal gates. NAND and NOR are called universal gates because you can get any implementation using these two gates. Then we talked about simple truth table, how to read a Boolean function from the truth table, how to simplify it. We can have simplification using Boolean algebra. We can also do simplification using Karnaugh maps. We can also do simplification using computerized methods. Quine-McCluskey is one of them, but we did not discuss that in great detail. We also talked about sum of products and product of sum. When you write a expression, it can be as a AND gate, series of AND gates with one OR gate, or series of OR gates with one AND gate. This is called, the first one is called sum of products, second one is called product of sums. So we have done all this. Today towards the end I will give some examples. Actually the first homework is on the website, second homework is also on the website. I do not know whether it is allowed, I have already sent it, maybe it is there or maybe it is going to be put very soon. So today I will do some problems from the second homework sheet just for a revision purpose, especially for those who are new. Before closing last time, I talked about what are known as the MSI gates. We classify the gates based on the complexity. Simple gates called SSI, small scale integrated circuits. The complexity of these circuits is very small. Then we have what are known as MSI circuits, MSI gates or MSI ICs. MSI stands for medium scale integrated circuits. This will have functions which are much more complex than the small scale integrated circuits. Usually we have a sort of a thumb rule which is not a very rigid rule, it is not a mathematical rule. Small scale integrated circuits which have about 10 gates, up to 10 gates. A gate is a simple, you see not everything has to be a gate, but we always say in terms of gate complexity. Even a microprocessor, we can say it has 10,000 gates. Does not mean that 10,000 gates are connected into microprocessor, there are other modules, but it is equivalent the complexity wise. So, small scale integrated circuits, actually we talked about hierarchy. Hierarchy means a digital system is something like a computer or a microprocessor or a DSP or a cell phone. These are all digital systems. These are higher level. Below that are what is known as subsystems. Take a microprocessor, it has memory, it has input output unit, it has arithmetic logic function. These are all subsystems. From subsystems you go down to the modules. Arithmetic logic unit is a one subsystem, but it contains arithmetic circuits, logic circuits. And below that we have the gate level implementations. How do you make a adder using a gate? We will see all those things in the next few lectures. Below that, which we do not see in this course, but a person who designs these circuits, a person who designs these ICs should know it comes from basic transistors, because nothing is built without transistors. A NAND gate will have transistors, about 10. What is a transistor? It is a CMOS today. Earlier it used to be a BJT, bipolar junction transistor. So these transistors are the basic building blocks or basic units, but this is required only for design and simulation and all that. Since this course does not involve those things, we did not talk about. So for us this course, the minimum building block is gates. From gates to modules, modules to subsystems, subsystem to systems. So everything will be expressed in terms of complexity. A small scale integrated circuit like a gate, AND gate, OR gate, these are all small scale integrated circuit. Later on we will see flip flops, these are also small scale integrated circuits. This will have about 10 transistors, 15 transistors, something like that. Again, this is not a very rigid number, do not take these numbers very seriously, just to give you an idea of the complexity, idea of the how complex the circuit is. Up to 100 gates, we call it medium scale integrated circuits. We talk about multiplexers, that is the topic of today and the next 2 or 3 days. Multiplexers, decoders, things like that, adders and all that. Then you come to large scale integrated circuits up to 1000 gates, memory systems as an example, some peripheral devices used in microprocessors. And then we have the VLSI, very large scale integrated circuits, which is about more than 1000, but today 1000 is a very small number. Today's microprocessors and DSPs and cell phones and any digital system is so complex. It contains easily 10,000, 100,000, even 1 million gate levels, gate functions. So this is how it is. So we finished our small scale integrated circuits, we talked about gates, we talked about how to make circuits using gates, we talked about simplification of these gates, we talked about sum of products, we talked about product of sums and all that, how to use Boolean algebra to reduce, how to use corner maps to reduce, all that we have seen. But yesterday towards the end, the last class towards the end, a few minutes or maybe about 10-15 minutes I spent on medium scale integrated circuits. Medium scale integrated circuits have an advantage, we do not go to gate level simplification. These are circuits, you see even a gate, take a transistor, take an AND gate, OR gate. As I said, they are made of transistors, but we do not build them, we do not take transistors like you do in analog circuits lab. You build a circuit using transistors, solder them or use a breadboard and do that. We do not do that. This is done by manufacturing process, VLSI or IC design and manufacture is a huge field. The reliability of the circuit is very good because it is all done chemically, etching is there are lots of steps, we are not going to go through all that here in this course. Large number of steps to make sure these circuits are reliable. They will not snap. If you build a transistor circuit using breadboard or soldering iron, there is a possibility it will snap or there is a possibility it is a dry solder. it will not work. But these ICs are not like that. ICs are manufactured using a chemical process. There are lots of processes we are not going to discuss today, very high technology is there. Earlier there used to be etching and ion doping, implantation and all that. Today it is all electron beam lithography, molecular beam lithography and all that, very advanced. These are so reliable. When you come to MSI again, these are made of single ICs. So when you say MSI, like a full adder is an MSI. A full adder is made up of a circuit which is made very nicely using this chemical process, using the manufacturing process, so that they are very reliable. You make, of course there is a lot of testing going on before it is given out for sales, before you can buy it, they go through a large number of tests. Assuming it is all passed all these tests and it has been successfully found to be good, after that it is very difficult to spoil it, unless you put a fire on it, or a 5 volts IC you apply 100 volts, 200 volts, unless you abuse it purposely. These are very reliable circuits. What is the advantage of this? We already talked about it in the last few lectures. Many advantages. One is the cost. When we build small ICs like that, put them together, there is a lot of expense. Whereas when you buy an IC which is all integrated already, integrated circuit, the cost is not proportional to the complexity. If a SSI costs, let us say 10 rupees, even 10 rupees is, I think is not there today, even cheaper than that. 10 transistors, I said SSI. 100 gates, up to 10 gates I said SSI. Up to 100 gates is MSI. 10 gates is going to cost 10 rupees, 100 gates is not going to cost 100 rupees. It may cost 15 rupees, maximum 20 rupees, depending on the complexity. So cost saving is there, reliability is there, and when you put them together in one power supply, the amount of power that is consumed is also very low. Today it is a very important area, power consumption, because you have all these laptops, cell phones. This cannot, of course you have to charge them every day, but then if it is going to consume huge amount of power, first of all you can't put it in your pocket, it is so hot, and you can't hold it in your lap and then do the computation. So these are the reasons. Power consumption is reduced, reliability is increased, cost is reduced, size, amount of space it takes. Yeah, I don't want to have supposing I want to have a earphone, I mean not a earphone, I say hearing aid. You don't want to have a big thing hanging in your ears. You want to have a small IC. So many of these people who have this hearing aids do not like others to know that they have it. It will be so small, it will be inside. All these are advantages: small size, high reliability, low cost, and low cost, low power consumption. So in that direction we are now moving from today. We will talk about MSIs. Medium scale integrated circuits, MSIs. As I said, then approximately up to the 100 gates, approximately. Don't count the number of gates and say it is only 75. It is not MSI, it is not like that. Up to 10 it is SSI, 10 to 100 is MSI. Now, there are several of them. We will study first multiplexer. Sometimes it is called MUX. MUX is multiplexer. Now, what does it contain? It contains several inputs. When you come to MSI, LSI and all that, you drop your gate symbols. Up till now, we are drawing gate symbols. All the circuits we drew, we had symbols of the gates. From now on, we will not do that. black box. Now several inputs, I will say 4 to start with, and one output. So I will call this I0, input 0, input 1, input 2, input 3. In digital it always starts with 0. 0 to 3 is 4. And then one output we will call it F. The multiplexer property is one of these inputs will be connected to the output at a given time. I have several inputs, one at a time has to go at the output. Now the question is, there are 4 inputs. How do I know which input goes to the output? So there are other 2 signals called selector signals. We will call this S0, S1. S stands for selector, I stands for input, F stands for output. So if S1, S0 is 2 inputs, they can have 4 values, 0, 0, 0, 1, 1, 0, 1, 1. If selector is, so I can now draw S1, S2, this is the truth table, we talked about truth table also. If both selectors are 0, F is I0. This is what a multiplexer is described as. You want to call it truth table, but truth table usually has, as I said, zeros and ones at the input and zeros and ones the output. So if you want to call it function table, does not matter. So this is the function table multiplexer. It is not necessary that only 4 outputs are not, or 4 inputs and 1 output. I can have 8 inputs, it should be power of 2. I can have 2 inputs, 1 output, 4 inputs, 1 output, 8 inputs, 1 output, 16 inputs. Okay, I can also have 32, 64, but then after that the size becomes limited. I can build a 32 to 1 multiplexer using smaller multiplexers. We will see that later. Now 2 to 1 multiplexer will have 1 selector line. This will have 2 selector lines, as we said, this will have 3, this will have 4. If it is really 2 inputs, I should select either this or that. I need only 1 input as selector. If I have 4 inputs, I need 2 inputs as selectors because it has to be 0, 0, 0, 1, 1, 0, 1, 1. 8, of course, I need 3, S0, S1, S2, S1, S0, 0, 0, 0, 0, 0, 1, etc., 1, 1, 1, like that. So in order to qualify this, you cannot simply say mux, I should say it is 4 to 1 mux, 4 inputs and 1 output. I should always say a multiplexer with a qualification, 4 to 1, 2 to 1, 8 to 1, 16 to 1. Now where is it used? Multiplexer. As I said already, several inputs and 1 output. So one of those inputs should be available at the given time. The display may be. There are several things and 1 input, 1 will be available at a given time. Selectors. Suppose I have 4 signals and only one signal should go to the output. Which signal will go to the output depends on these 2 selector lines, then I use a multiplexer. So what is contained inside? As I said earlier, all circuits in digital are made up of AND or invert, including the flip-flops and other things we are going to study later. AND or invert is the fundamental gates. I can also have universal gates using Nand or NOR. Now we are now saying F is S1 bar, S1 bar, S0 bar, and both are 0, I0. When both are 0 and input is 0, input is I0, I will have it, or I1 this is the equation, Boolean equation. This is the function table. If you want to call it truth table, I have no problems. This is a function table, function equation or a Boolean equation. Because we have the gates, remember gate we had a symbol, a truth table and a Boolean function. Here there is a symbol, function table and a function. This will be maintained throughout. Whatever you study will have these 3 components. Now, what does it mean? It is an AND gate. I give an AND gate with 3 inputs. I give S1 bar and S0 bar, I0. So this will be translated into, inside this what is the function, even though we do not have to show it, but you should know what is inside. You should know what is inside. Inside this is, there is an S1 bar, S0 bar, I1, I0. Then I have to draw this for S1 bar, I am sorry, S1 bar. S1 bar, S0, I1. Then S1, this is S1 bar, S0. This is S1, S0 bar. Do not worry about copying the circuits, every textbook will give you all these things. So do not try to copy and make a mistake. These are all available in any textbook. The textbook you already suggested, Mano, Roth, Tossi, Weckerle, many books. This is another AND gate. And 4th AND gate will be, I will not draw this, I will draw like this. S1, S2, I3. At one time, either this is true or this is true or this is true or this is true. Not all of them. That is what it means. Either this combination plus is an OR. Either this combination or this combination or this combination or this combination. So that means I should tie them with an OR gate. This is my F. So inside the multiplexer, I have 4 AND gates, 3 inputs, 1 OR gate, 4 input and 2 inverters, one for IS0, the other is for two inverters, 4 AND gates, 1 OR gate that make the inside of this. But you do not have to draw this every time. If you put it like this and say 4 to 1 mux and give S1, S0 and I0, I1, I2, I3, everybody understands what it is. That is the advantage of now we can have 2 to 1 multiplexer as I said, 4 to 1, 8 to 1, 16 to 1, and as I said this is used for selecting one of several inputs at a given time based on this. The reverse of this is called demultiplexer. I have one input and 4 outputs and 2 selectors. Based on this selector, this output will be connected to this this input will be connected to this output, this output, this output. I will show that to you now. A demux we have one output, one input, I will call it I, and F0, F1, F2, F3, again based on 2 selectors. If this is 0, 0, this input will be connected to this output. 0, 1, this will be connected to this output. 1, 0, this will be connected to this output. 1, 1, this will be connected to this. So I have a single output connected to many, single input connected to many outputs, one at a time. This is used in displays. For example, you have display, the input changes, but displays will be 4 displays. First you give the display have to correspond to this, second you give the display correspond to this, third this and this. And displays are usually have a persistence of vision. By the time you finish and come back, it will still be glowing. That is what is done usually in a multiplex based display. Now put them together, mux and demux. I have a 4 to 1 mux and a 1 to 4 demux. This is F, I will call this as F also. So I have this S1, S0, here also S1, S0. So if I want to send this, I want to send this input into this, I select S1, S0 here as well as S1 here, 0, 0, 0, 0. So this is a mux demux combination used for signal transmission. Several signals, at any given time one of those signals should reach a destination. A simple example will be telephone. Of course, telephone is much more complex than this. Suppose you have 4 lines and 4 telephones. You do not run 4 lines from exchange to the individual subscribers. You do it with 1 line. So this subscriber will be connected to this subscriber if this is selected. So 2 extra lines are required. We have not saved much. 4 lines, instead of connecting 4 lines to 4 lines without multiplexer, I can do that. Without multiplexer, I can have 4 inputs I0, I1, I2, I3, connected to 4 outputs I0, I1, I2, I3, 4 lines will be run, no hardware multiplexer. Now I am having 2 hardware multiplexers plus 2 extra lines I have to run, but this is only an example, nobody uses for 4. Suppose I have 16, 32 inputs, 32 input here and 32 output here, 32 will require only 5 selector lines. I have 5 selector lines, 32 signals can be connected to 32 destinations. That is saving in hardware. So all these simple examples in the class will tell you what is it, but the real practical application will be much more complex, much more involved. Now, I told about multiplexer and demultiplexer, what is the use, how to select the lines from here, how to select the lines there. I also said several higher level multiplexers are available because 2 to 1, 4 to 1, 8 to 1, maybe even 16 to 1 is available, but beyond that it is going to be difficult to build a hardware. So what we do is, we do what is known as a multiplexer tree. Suppose I want 32 to 1 multiplexer. How many selector lines? 32 means 5 selector lines. I can have a single multiplexer with 32 inputs, 5 selector lines and 1 output. As I said, it is cumbersome to make an IC, simple IC. Of course, big complex ICs are available today. Hundreds of gates, thousands of gates, millions of gates. We are not talking about those things. In simple ICs, SSI, MSI, what we do is, we can have 4 8 to 1 max. Eight to 1, like that I am going to, no, not the same thing, different, sorry. So like that there will be 32, I am not going to draw everything. 8 to 1, 8 to 1, 8 to 1, 8 to 1, 4 times 81, 8, 32 inputs are available. This will have one output, this will have one output. This will be fed into a 4 to 1 multiplexer. An output will be selected from here. This will be my F. This will have 3 selector lines, 8 to 1. So 2. So totally 5 selector lines, 3 will be here, 2 will be here. Suppose I want input number 17. F should be I17. I want input 17 to be the output. This is input 0 to 7. This is input 8 to 15. This is input 16 to 23. This will be 24 to 31. 0 to 31 is 32. 32 inputs divided as 8, 8, 8, 8. Input 17 is this. In order to select this 17, I should give, this is 0, 0, 0, 0, 0, 1. So this will be S2, S1, S0, S2, S1, S0, S2, S1, S0, S2, S1, S0. So S2, S1, S0 should be 0, 0, 1. If you select 0, 0, 1, the second input of the third multiplexer will be selected this line. At the same time, the second input of every multiplexer will be selected. So I will have 4 inputs to this. Second input of this multiplexer, second input of this multiplexer, second input of this multiplexer, second input of this multiplexer. All the 4 will be available. But I don't want all of them, I want only one of them. That is where I use the second selector now, S4, S5, S5, S4, I am sorry, S4, S3. Now S4, S3 should be, I want only this, the third input. Even though 4 inputs will be selected to the input of the 4 to 1 marks, I want only the third one to go out as I17. This is not I17, this is I2, I1, this is I1 which I do not want, this is I9 which I do not want, this is I17 which I want, this is I25 I do not want. Out of 4 inputs I1, I9, I17, I25, only I17 has to go. That means I should select this S4, S3 such that it is, this is 0, 0, 0, 1, 1, 0. If I make S4, S3 as 1, 0, the third input which is I17 will go out. So now this will be, selector lines will be 0, 0, 1, S0, S1, S2, S3, S4, 0, 0, 1 will select I17 along with I1, I9, I25, out of which I want only I17, which means I should select this as 1, 0. So this is my selector combination so that I17 gets through. Such a thing is called a multiplexer tree. Multiplexer tree. So multiplexers we saw what a multiplexer is, several inputs and one output. How to select the output depends on the selector lines. We can have 2 to 1, 4 to 1, 8 to 1, 16 to 1, 30 to 1, whatever. And we saw demultiplexer, which is one of this one output, one input going to several outputs. So by synchronizing the multiplexer and demultiplexer, we can select one of the inputs as corresponding output. We also saw how to connect a series of multiplexers called multiplexer tree so that a large multiplexer, because up to 16 to 1 is possible in small scale, medium scale ICs. Medium scale ICs I defined as anything less than about 100 gates. Beyond that the number of gates will increase, so it will become very cumbersome. If you want to have one 32-1 multiplexer, there will be 5 selector lines, 5, 5, 5, 5, 32 into 5, 5 plus 1, 6 input gate AND gate, 6 input AND gate, 32 of them connected to OR gate, which is also very large. We do not want that. That is how we do it, this way. Are there any questions? Anybody has a question, please raise your hand. Nobody has any questions? If you raise your hand, I will ask them to unmute. Okay, unmute Ayush. Mr. Kannan, Ayush has a question.
Sir, in that multiplexer tree,
Yeah.
Sir, you wrote that the selector lines S4, S3, S2, S1 and S0.
Yes.
Sir, how did you decide that which S0 would be 1 or S0 would be 0?
It is generally, this is a lower level. This multiplexer is a lower
The
level. So use the first three
Yes.
selectors S0, S1, S2. This is a higher level. So
So, but
use
sir, S0 would be 0 or 1. How to decide that? It would be
no.
0 or 1.
S0, S1, S2 will have 8 combinations, right?
Yeah,
So
right.
the first combination is 0, 0, 0.
Yes.
Second combination is 0, 0, 1.
Yes,
Now
sir.
I17 I wanted. 17 is the second combination of the third multiplexer.
It
Correct?
will be 0, 0, 1.
Yeah, that's what I said, 0, 0, 1.
Sir, so in the answer you should write 1, 0, 0, 0, 1.
Oh, okay. There you go, man. You are very smart. I'm sorry. You are right.
Okay, okay. That
Yes, yes. Thank you very much. It should be
Okay, sir.
001.
That okay.
That's what you had a question, right?
Yes, yes, sir.
Very good. And somebody else here, this corner?
Hello, sir.
Yes, tell me.
Hello, sir. Can you
Yes.
hear me, sir?
Yeah, I'm hearing you. Please tell me.
Sir, in 32 multiplexer, we have used 8 to 1 multiplexers, no, sir.
Yeah. Yes. I can
Instead
also
of
use.
that, can we use 16?
Yeah, exactly. I can use 16 times 2 and 1 2 to 1. I can use 16 to 1, 2 of them, and 1 2 to 1. I can
Yes,
also
sir.
use that. You are right. This is 16 to 1, 16 to 1, and I get them into 2 to 1. In this case, I will have 4 selectors here and 1 selector here. Totally 5 selectors are required. Okay?
Which is better of both of them, sir? Which is better,
Depends
sir?
on the
Both, in
availability.
that both.
Depends on the availability. 16 to 1 is rather not used that much. 8 to 1 is ideal.
Oh,
But there is no
okay.
rule. There is no rule on that. Yeah.
Okay.
Whichever is convenient, whichever is available, whichever is comfortable with, you can use. Yes.
Okay.
Okay. Any more
Subhashish, do
questions?
you have anything to ask, please?
Anybody else has a question? Raise your hands.
Subhashish?
No, sir, I don't have any question.
Very good. We'll move on. Yeah, that is a good one. I suggest pointed out. See, other than selecting signals, from several sources to one output and one input to several sources, there is one other nice interesting way of using multiplexer. Multiplexer can also be used to do a simplification of Boolean functions. So I am going to do now use of multiplexers to logic simplification. Use of mux for Boolean simplification.
Hello.
Yes, sigma m, you know what it means. The following minterms are present when I say sigma m, and I will use 4 variables. F of ABCD is sigma 0, 1, 5, 7, 9, 12, 13. Simple, anything, arbitrary. I have no functions in mind, I just wrote arbitrarily. What do you do? How do you simplify it? I draw a corner map using 4 variables, correct? 4 variable corner map. This is 0, 1, 1, 0, 1, 1, 1, 0. Now what are the functions, minterms present? 0 is present, 1 is present, 2, 3, 4, 5 is present, 6, 7 is present, 8, 9 is present, 10, 11, 12, 13. These are the minterms present. This is the mapping of the minterms of this function onto the 4 variable Karnaugh map. Okay? Now, usually what you do? You try to make this as one prime implicant and maybe this as one more and maybe this as one more. Usually, if I did not say use multiplexer, if I had not said use multiplexer, I would have written one prime implicant here, one prime implicant here, one prime implicant here, and maybe one here, 4 prime implicants. And corresponding terms I would have written, got the gates and connected the gates. Now I am going to use a 4 to 1 multiplexer. It has 4 inputs. One output F and 2 selector lines S1 and S0. What I am going to do is, I am going to select 2 of these 4 variables as selector variables. I can use AB or CD, or I can use AD, any combination. AB, CD, how many combinations? 2 at a time. I can have AB, CD, I can use AB, I can use AD, AC, I can use AD, I can use BC, I can use BD, I can use CD. Any of the 2 variables, any of the 2, any combination of 6 I can use. To make it life simple, to make the life simple, I will use AB as the selector variables. That means AB can have 0, 0, 0, 1, 1, 0, 1, 1. These are the 4 combinations possible in multiplexer: 0, 0, 0, 1, 1, 1, 1, 0. Now, when AB is 0, 0, this will be the AB 0, 0, correspond to these ones, I will have to connect this output. Now this output is C is 0, D is 1, so this is C. I only look at one slice of the, I look at only one slice of the Karnaugh map now. This slice corresponds to AB 0, 0. Please listen carefully, this is very important. One slice of the Karnaugh map, which is 0, 0, that is used, and there I have to simplify. Now it is 0, CD is 0, 0, this is 0, 1. So 1 goes, D goes because this 0, this 1, C remains as C bar, C bar. Second slice is 0, 1, correspond to this, correspond to this, C is 0, C is 1, D is 1, D is 1, so this is D. Third one, you have to be careful here. In Karnaugh map we do 0, 0, 0, 1, 1, 1, 1, 0. The multiplexer, it is 0, 0, 0, 1, 1, 0, 1, 1. I2 and I3 have to be switched. That is a common mistake people do. In Karnaugh map you do 1, 1 and then 1, 0 because of obvious reasons you can combine these ones as prime implicants. Whereas multiplexer we use 0, 0, 0, 1, 1, 1, 1, 1, 0, 1, 1. So this has to come first and then this. So, this 1 0 corresponding to only one term C bar D. And finally, it is 1 1 C 0 C bar. So, now this F is same as this M, whatever is the, whatever you get out of this using 4 prime implicants, this plus this plus this plus this, I am able to get using a simple 4 to 1 multiplexer. And how many gates? C bar, one inverter, same inverter, D is there, this is C bar D. So, we will have one AND gate C bar D, one inverter for C bar. So, I need one 4 to 1 mux, one inverter for C bar, one AND gate for 2 input AND gate. For C bar D. This is my logic. As I said, the cost is not proportional. A multiplexer does not cost 10 times as a gate. A gate may be, I do not know the cost now, gate may be 5 rupees or even less, multiplexer may be 7 rupees. How much I have saved? If I had used this, I would have used a 2 input AND gate with inverter, a 2 input gate, another 2 input gate, another 2 input gate. So, I would have used 1, 2, 1 2 input AND gate without multiplexer, 1 2 input AND, this is this would be 3, 1 2 3, 3 input AND, this will have 3 input, this will have 3 input, this will have 3 input, 3 input AND gates, 1 inverter for C bar, this was C bar, this one will be A bar. So, 2 inverters, and finally these 4 terms will be combined using an OR gate, 1 4 input OR gate. One 4 input OR gate, 1 2 input AND gate, 3 input AND gates and 2 inverters. Here I use 1 inverter, 1 4 to 1 max, 1 2 input AND gate. Not only it is, do not worry about the cost or power, everything is low. As I said, reliability is more, power consumption is less, cost is less, size is less. But more than that, it is very elegant representation of the Boolean function. I can use now, if you have some time, want to play with this a little bit. You use all these 6 variables as inverters. Each time the number will be different. If I use AB, if I use AC, if I use AD, BC, BD, CD, each time the map will be different. So, this will be different. Which of these 6 combinations will use minimum number of hardware? Which of the 6 combinations, this is a homework, I am not going to do it. Which of these 6 combinations of selectors AB, AC, AD, BC, BD, CD will result in a minimum hardware use? All of them will require 4 to 1 multiplexer. Other than that, number of gates, we have used 1 inverter and one 2 input AND gate. Is there anything less than that possible or more than that possible? You can just select that. That is only an exercise, you do not have to do it very seriously. That will give you some feel for the whole problem. I will do one more of these problems before going to the some of the revision homework. Why don't we do this? F is xy wxyz sigma m two 3 10 11 12 13 14 15 I do not know. I have a function with 4 variables xy, w, xyz. Sum of min terms is 2, 3, 10, 11, 12, 13, 14, 15. Let us do a multiplexer based solution. 4 to 1 multiplexer. You always have to write size of the multiplexer on the top, 4 to 1, S1, S0, 4 inputs, I0, I1, I2, I3, F. Now, let us map this function 0, 1, 2, 3, 4, 5, 6, 7 is not there, 8, 9, 10, 11, 12, 13, 14, 15. This is also very simple, even as a function. Without multiplexer, this should be without multiplexer. This color is not good. Without marks, F would be this one, which is Wx. These 4. That would be x bar y. Very simple. So it is not always that multiplexer gives you the simplest possible solution. I just took this example to show you without marks I have only this Wx x bar y. X goes through an inverter, This is Wx, x bar y, OR gate. Without multiplexer, I am having two input AND gates, one 2 input OR gate,
Okay, sure.
one inverter.
பரவாயில்ல இப்படியே ஆன்லைன்ல இரு.
Without multiplexer is a very simple elegant solution. I just want to show you that this is also possible. Not every time you have to rush for multiplexer. Whereas if we do the multiplexer, I will use again Wx as the selector variables. This will be y. This will be 0 because no input, 0. This will be 1, all are 1s. This will be also W, Y. Now which is better? Tell me. In one case I am using two input AND gates, one 2 input OR gate, one inverter. The other one I am not using any gate. Y is available, 1 is available, 0 is available, only 1/4 to mux mult, 1/4 to 1 mux. This is hardware requirement using multiplexer. This is hardware requirement without multiplexer. It is very difficult to choose. Again, as I would use a 4 to 1 multiplexer solution because it does not require any extra gates. Y I can connect directly, 1 I can connect directly, 0 I can connect directly. 0 is 0 volts, 1 is 5 volts, assuming you are 5 volts operation. So whichever is possible, this is also good. This is also not a bad solution. That is a very good solution. You can use any one of them. Okay, I am going to stop here. We will continue with this MSIs next time. We will talk about what is known as the decoders and encoders. Before that, I want to ask you if there are any questions. Otherwise, I will try to do some 1 or 2 problems on the tutorial sheet number 2, which is on the, I do not know whether it is in the website. It is going to be in the website very soon. I have already sent it to the NPTEL office. Yes, you have a question there? Somebody has a question? Yes, please.
Yes, sir. Hello, good evening, sir.
Yeah, Subhashish, ask me.
Yes, sir. I was asking that is it the only use of mux or anywhere else mux is used?
I told you this is one of the uses, but then the many use is that I said several inputs and one output. Telephone exchange, I gave you an example. Suppose you have 32 lines and 32 subscribers. Will you run a line from each subscriber to each destination? No, we will have only a few lines. So one of them will be selected at a given time, the other one. That is one simple example. There are lots of applications in multiplexers. And also supposing the display, I gave you an example. Suppose I want to have a display in the bank, 4 different counters. One multiplexer will give a display from one of the tellers. Second teller will have the second, but then we will have only one multiplexer because display will persist for some time. It is called persistence of vision. So when you have one line, first you refresh one display, then you refresh the second, then third and fourth and come back to first, it will still be on. Because we have this persistence of vision. When you have a display, it goes for some time, does not immediately go back, go out. Lots and lots of, the multiplexer is one of the very frequently used hardware. We will see many of the multiplexers later on. This is already I gave you 2 or 3 examples of applications. Later on we will see some more. When we do design the sequential circuits, we will again use multiplexers. Anyway, Aruna's question I am not able to read, sir. They are putting a question on a piece of...
No, sir. I just suggested Arunai to keep the paper little away from the camera because they kept it too close to the camera.
Otherwise, they can chat with you and you can read it for me.
No, not chat, but they can in fact share a PowerPoint presentation or a paper of questions with me.
Yeah.
There won't be any problem. Instantly, we can see them.
Arunai.
Aruna, if you can type your MS Word or something on a small question, see the third icon on your window.
Yeah,
That
Arunai
is a
has got a
share
piece of
option
paper
there.
now. Now he has put a color
Yeah.
there. You may be able to read it.
Uh,
Are you able to read it? Don't move it.
it says
Yeah.
applications of MUX
Ah.
and DMUX.
Yeah, I told you all the time I have been talking about multiplications, applications of
Yeah.
mux and demux together form a nice combination of selecting one of several signals. I have several signals at the source and I have several destinations, but I don't want to run one line
Just
from
attend on
each
India, please.
source
You
to
attend
each
on India.
destination.
You are an electrical lights person here.
I will use,
Lights
now you
ಎಲ್ಲ
are able to
ಪೋಲಿಸಿ.
hear me, right? You just wave your hand. Arunai, are you able to hear me? Just wave your hand. Yes. So several sources, several destinations. One way is to run several lines. The other way is to have a mux, select one of the several sources, send it through a line, and then the output you send it to the appropriate destination. Of course, you need to run some selector lines from here to here, but that will be very appreciable only when the number is very large. The example I gave you was 4 to 1 and 1 to 4, two selector lines. It is not a great advantage. One multiplexer, one demultiplexer, two selector lines running from source to destination. It is not a good idea, but this is only an example. In practice, you have several lines. For example, telephone exchange will have 1000 lines minimum, and there it will be very useful. That is one thing. Second thing, as I said, display. Just now I explained to this gentleman, display, refresh display. If you run one several sources, like a bank teller is an example, you have several tellers having different numbers calling, and each number will be displayed by one line. Multiplexer can choose one of them and display it, then the second line will display it, third line will display it, fourth line, because this is your persistence of vision, whatever you displayed first will still remain when you go back to the first again. This is one example, and this is another example, the simplification of logic functions. And there are many more we are going to see in future. You can also read from books. And multiplexer trees I told you. Multiplexer is one of the very elegant topics and it has lots of uses. See, the many hardware that are used constantly in combinational logic. We have not discussed sequential logic where flip-flops will be used. In combinational, whatever we have studied so far, exclusive OR and multiplexers are the most frequently used hardware. Exclusive OR gates, we have not seen them, we will use them in the adders next time. Exclusive OR gates and multiplexers are the most commonly used combinational logic building blocks. I think I have answered Arunai's question. Now, if there are no questions, I am going to ask you a few questions from the topics we covered last time, up to last time, not last time. So, let us see how many of you are prepared.
I have one question, sir.
Yes, you have a question. Yes, please.
Sir, that you said the application of MUX in the telephone exchange and the another one display.
Yeah.
Tell that in diagrammatic ways, sir, because
Huh?
we can't imagine. We can't imagine, sir. Please tell that in diagrammatic.
Come on, it's only an example. I say nowadays nobody uses all those. Nowadays, today we have this crossbar switches. Just to give you a
At least
simple
tell that.
idea. Huh?
At least tell telecommunication, telephone exchange that in diagrammatic.
Telephone exchange, they don't use it now. I gave you several sources, several destinations. That is all. I have several signals. One of them has to be connected to one of the destinations. I have several, let us say 100 sources and 100 destinations. One way is to run 100 lines. And if you want, in fact, the telephone exchange is even more complicated. 100 numbers, 100 input, I have to run one line from each of these to all the 100 numbers. How many lines will be there? Every subscriber has to be connected to every other subscriber. Imagine the number of lines. Now I have a selection mechanism. That is all I am saying. Don't take my things very seriously. You study, I say. You have to go and study in the books. and Google it and tell me the answer instead of asking me to tell you everything. Yes, yes please, Ayush. Ayush.
One second, Ayush. 1 second, Ayush. Let me unmute you. Yeah, go ahead, Ayush.
Sir, you just asked that question that which combination will require least hardware.
These two.
Sir, I think the one we used, that AB combination, will give the least hardware.
Very good. I did not choose it. I just selected it and it became very good. Thanks. So you have checked all the 6.
No, I didn't check that, but I thought that first of all, if we will choose any two random from ABCD,
Yeah.
any two combination, then the combination that will give the least require the least hardware will be the one which has most minterms which are close to each other.
Yes.
So
You are right.
so they have the least literals
Yes.
in each term.
Correct. You are right. Good. Anyway, now I am going to ask you one question now. All of you. You are supposed to work it out. Can you draw an exclusive OR gate using only NAND gates? I told you how to use NAND gate and NOR gate as universal gates. The question is, this is one of the questions in your second assignment sheet. I choose some questions at random from assignment sheet and work them out. So you know. Draw exclusive OR gate using only NAND gates. Very simple. Do it. 1 minute. Tired after that. 1.5 hours is too long. Anyone? Raise your hand. I am the one to raise the hand, nobody else.
Yes, you are the only one raising hand, sir.
Simple questions are so long it takes. Okay, I will do it. An XR is A bar B plus AB bar. So I have 2 inputs AND gate, 2 of them connected to an OR gate. This is F. This is A bar B. This is A B bar. What is the problem here? What is the problem? Very simple. Now, you know how to get an OR gate, inverter using NAND gate. This is A, this is A bar. This is B, this is B bar. So this inverter will be replaced by this. This inverter will be replaced by this. This inverter will be replaced by this. Okay? Here is the problem. I told you the bubble theory. Put a bubble here and input bubble, they get cancelled. this is a bubble, this becomes NAND, AND becomes NAND, AND becomes NAND. I can't leave a bubble here because this is also has to be, because when I invert this, I should also invert this, bubbles get cancelled. I invert the output of this gate, this also will be inverted, input of this. But this is an AND gate, this is an AND gate, 2 input OR gate with inverted inputs also is a NAND gate. So this is equal to this is my F, A, B, A bar B, this is B, this is A. This is a 2 input exclusive OR gate using 1, 2, 3, 4, 5 NAND gates, 5 NAND gates. Here also you need 5 gates, 1, 2, 3, 4, 5. 2 inverters, 2 AND gates, 1 OR gate. Without NAND, if you want to do that exclusive OR, 2 input OR gates, 2 input AND gates 2, 2 input OR gate, 2 inverters. Here except inverters, this is 1, 3 NAND gates and these 2 are 2 NAND gates, totally 5 NAND gates. As I said, NAND gates is equal to easy to make in design and manufacturing, so we use this all NAND gate solutions. That is why it is called universal gate. One last question before I close for today, again from the tutorial sheet, from next assignment sheet number 2. Implement using product of sums. POS means product of sum, that is OR gate followed by AND gates. Expression for F A B C D sigma m do it quickly. 1 more minute to go. Anyone who is finished can raise the hand, otherwise I will do it after 2 minutes. Don't expect me to do all the problems myself. Next time onwards I will give the problem and you have to do it yourself. It is very easy, these things are very easy. Of course, I can understand those people who joined today. Some of them they may not know what I have taught, but others. And next time you have no excuse because I am going to continue.
They also have to view your lectures on the NPTEL website, sir.
Yeah, they have to. They are not doing it. Okay. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, very beautiful here. This is one prime implicant. I will have colored chalk. This one prime implicant. This is one prime implicant. These four corners make one prime implicant. So this is 1, this is 2, or this is 2 corners. This is 3. So F is B bar, C bar, these corners will be B bar, D bar, this will be A bar, C, D. Yes? This F I wanted, this is product, sum of products. But I want POS. For POS what I do is, what do you do? Huh? Yes. Tell me. Hello? Yes, sir. You are not able to mute, unmute. He has to be unmuted.
Yes, sir, I have unmuted everyone.
Yeah. Tell me.
Sir, F bar, F bar. Sir, if
F
we
bar.
take complement, yes, sir.
F bar.
Sir, B plus C.
Correct? This is F
Yes,
bar.
sir.
Then you have to simplify it. This is F bar, but I want a F.
No, sir, that last one was F bar. This one will be F.
No, this is not F bar. This is F bar. This is F, this is F bar. If I use ones, if I use zeros, I can directly get F in product of sums form. This is F bar in product of sum form. We will do further simplification, but it may not come in product of sum form. So I need to use this one, this one, this one. Again 3 terms, right? This one will be C bar, D bar. This one is C bar, D bar. This one would be B, C bar, B bar, C. Then this one would be A bar, B bar. If you simplify this, you should come to this. Otherwise, you can directly read it. You can directly use zeros to read it in product of some form, or you do F, get us De Morgan's, you get F bar. Depends on what you want. If you want to sum of product, you can simplify it. You don't have to use here. Otherwise, you have to do this way. Both are right. Okay. Any further questions today? If there are no questions, I am going to stop. We'll see you on Wednesday. I am going to talk about decoders, encoders, priority encoders. You can read them. You can also listen to my lectures. I have already given you the schedule of NPTEL lectures. Go through my NPTEL lectures before coming to the class. It will be a great help for me and you. Okay then, I will sign off today. See you on Wednesday.
Hello.
Yes.
Hi. I just wanted to let all the participating institutions know that MOU hard copy, soft copy has been sent to them. We request them to get it signed and send the hard copy back to us.
There is an administrative announcement. There is an administrative assignment. Please announcement. Please do it. Very important. Okay.
That's
See?
the MOU which, okay, that's better now.
Yeah,
Now,
you gave the MOU that day, I know. Yeah.
yeah, we have sent the email soft copy so the colleges can sign it and send it back to us.
Yeah, download it, sign
That
it
is
and
how
send
we
it.
enroll all the students to the program.
Yes.
So it's very important. All colleges, please note that you need to send us the hard copy of the signed MOU back to the address that we have asked you to send it to. And have a good evening, all of you. Please go ahead with your discussions.
Ayush have a question. Ayush has a question. Ayush.
Yeah.
Sir, where should I, what should I do with the assignment solution? Should I mail it to NPTEL?
That one has not been clearly told to me. I think mentors will have to take care of that. Now, Usha Nagarajan may be able to explain that.
Yeah, I saw Ayush's mail. I saw your mail, Ayush. I didn't reply to you because we were actually not clear ourselves on what process we want to follow. So just give us few more days. We will set up a process in place, and then we'll follow those. Just give us a couple more days. So we will discuss and finalize on the process.
See, if the number is
For
very large,
individuals and
yeah. If the number is very large, it is better that the mentors do it themselves.
no, mentors will do for the students who are associated with the institutions. These are all individuals who are asking us.
Oh,
Yeah.
individuals, I think you can send. If it's a small number, we will be able to handle it. Anyway, we wait for the announcement.
Yeah,
Yes.
we just want to wait and see how many individuals are there.
Yeah.
Yeah.
So
Thank you
Ayush
all.
is
Have a good evening.
yeah.